Hello, welcome to video 48 in the lecture Advanced Mathematic Modeling. In the last video we discussed several examples of super diffusive random walks in 2D. So we could either have long-range correlated random walks where we have movements of persistent behavior, or we could have walks where the where the second moment diverges. For example, Levy flights where we have random directions, but step lengths were following a power law, and so we got this movements where the walker is rotating a lot with small step lengths in small areas and randomly doing these large displacements. And in this video now I want to discuss what these kind of walks have to do with optimal search strategies. Yeah? So first, what do we mean by optimal search strategies? So what is a search problem? Like many animals are confronted with the problem, so that they have in a certain target area there are some food items which are placed somewhere on the targets, and now we have the walker, and the walker can make some movement, but he doesn't know before where the targets are, and he has now to make a movement and try to find the targets. So typically we can assume that the walker has a certain search radius. So if the walker goes like this, then he will be able to find all targets in a certain distance around his movement. And now the question is, how should the blue trajectory, the motion of the walker, be optimized in order to find the maximal number of targets, or how to find the first targets very fast? Yeah? So the search problem, which movement yields the shortest time to find the target, or the maximal number of targets found in time. So this goes for like a bumblebee which wants to find flowers. This goes for lions or whatever predators who want to find their prey. But this goes also for a rescue. Maybe there is some people from an accident in the ocean, and you're with your helicopter and you try to find the people. And the question is how to systematically search the area in order to find the people as fast as possible. So typically we will have a search radius, as 0, so that's this distance here. Yeah. And so then you say like the walker has a certain areas, and then maybe he can find all targets in this radius, or he has a high chance to find them in this radius. This means he should maybe look several times. Like the helicopter really has the visibility, and now this depends, of course, the optimal problem depends, of course, so the solution depends on the number number and distribution, and the spatial distribution of targets. Depends on your search radius. It depends on the fact, for example, if you found the first target, is this empty and it's not worth to come to this again? Or is it a flower for the bumblebee that once you leave it a while alone, then it will refill and it makes sense at a later time to come back? So do you have destructive search? Or non-destructive search? So like, are the targets destroyed by when they're found? And then of course it depends on all the kind of cues, like if you're an animal in the desert and you want to find the water place, do you have any cue and have some idea about where the target would be? Otherwise, I mean, the general thing is, so in principle, so the rule of thumb is don't look twice in the same place. Yeah, because you looked there already. This means a random walk is maybe not a good idea if you make a movement like this. Then you look very often in the same place. You don't really go forward in time, and so you waste search efficiency looking often in a place you have been before. But of course this holds only if you always find the target. There might also be the case where you do not find the target, and there it might make sense to look in the same place again. Yeah, but this would mean then the best way would be just to follow in a straight line, always go straight. Then at least you always look in a place you have never looked before. But this has the problem you could leave the target area. For example, if you know your targets are in this width here and you just follow a straight line, will not be enough because you leave the area of interest. Or like, for example, if you know the accident was somewhere here and the people which might still swim in the water are thereby, it doesn't make for the helicopter just to follow a straight line. He has to come back here. Just a straight line. So a straight line might leave the area of interest. Now, if we know the area of interest very well, if it's really like this, then we could say maybe we do something like this. We go a systematic pattern. Yeah, but this you can do only if you know the area of interest. Now you could say, what about the other pattern? What is about doing a spiral? So we systematically try to find everything from our starting place, and so eventually we will go larger and larger somewhere. But here the problem is, this is of course a strategy which works well if you have a starting point. If you say, now I start and now I do a spiral. But so the first time point is special because like from later time points you don't do a spiral anymore. But often we want to have a strategy which is the same for all different time points. Yeah, and so so the question is, what is the best strategy? And this depends, of course, on all these things. If something like this makes sense, if you know the target area, of course, for if you have non-destructive research, it depends. Do you have a memory? It can remember where you have been before, and so on. So there's, of course, there is not a single solution which works always. The solution depends a lot on the fine details of the problem under investigation. But there is one thing which is quite frequent, very important in many of these variants of the search tasks, and that's the number of targets, or the density of targets. So, what's the special role of the density of targets? So this means, let's say we have a certain density of targets which are maybe randomly, maybe it, of course, this also depends on if you know any patterns about the distribution of the targets. Are they random or are they localized or something? But let's assume they're totally random, and so then the density of targets, we could then say, we could call this rho. And then now the question is, if you now have Walker, and you want to make now your walk here from a certain point to another point, you go in a certain direction, and as I said before, and now we assume we do here a straight line, then we have a certain search radius, and then the walker after time gets here a certain rectangle until he stops because he found the next target. And so we can look what is the typical distance lambda the searcher can do until, or he has to do until he hits the next target. So until the next target has a smaller distance than R0 to the position of the walker. And so that's the mean free flight or search distance. Lambda. So that sets the average distance that the walker can do until he finds the next target. And now one can, if you think a little bit, you can see that this distance is related to the density of target and the search radius. And in fact, this distance is 2 the search radius times the density. We need 2R0 because we can look in both directions, and then you see the rectangle, the area searched here, is proportional to lambda times 2 times R0. Yeah, and so this area search is then 1 over the density of the targets. So you see the mean free flight distance decays smaller when you have a larger visibility, and it's smaller if you have a higher density of particles. So this will then, of course, be a crucial ingredient if you want to know how long do you need how long do you have to move until you find the next target. it depends strongly on this distance. But now, when you now do numerical simulations, for example, if you have a search strategy and you want in the computer to see how would this perform, so we need an index to find the performance of our strategy. So you let your walker run according to the target, and now you need to know what's the search efficiency. And the search efficiency, call this eta. And so how can we define this? So first, first you have to see how do you find the target. So you have to make I do several things in the same step. First, I want to now explore a kind of Levy flight idea. So we want to look for a search strategy where we take certain steps in a straight line, and then we take steps in another straight line, then we do here steps and do another step. So we do steps in straight lines. And now I want to know how many of these steps do I want to do, and then I need to know what's the typical distance of such a step that I take. So we take steps of length L, and then we ask how many steps. We need n steps until the target is found. And then the search efficiency can be defined as 1 over the typical step length, so the average of the step length. So this here was L1, L2, L3, L4, divided by the number of steps that we need to do until we find the target. And so you can, if you think a bit about this, so this is 1 over the mean distance to the until the mean travel distance until the target is found. And the travel distance is the average distance times the number of steps. And so the smaller the mean travel distance of the walker, the higher the search efficiency. So, but maybe here I was a step too fast. Let's now explore in more detail how we want to construct our search strategy. Yeah, and we want to apply the ideas of the Levy flight. So we want I explore the Levy search, and so the idea is, so if a target is within the search radius, then the target is found here. So target is found. And if not, else we make a Levy walk actually. Let's make a step from a Levy walk. And this means we have here our walker. In the search radius here there is no target. Then we look for a direction, and then we take from our power law distribution, we take a certain step length, and then with constant velocity the walker goes in this direction. So make a step from a Levy walk with P of L proportional to L to minus alpha, or we call it mu here in this. So we make a walk with such a step length. So if now during the walk we find the target, we stop. Otherwise we go until we are at the end of this. And then we just take the next step. This might be in this direction. Then we make a walk with a new direction, a new step length, and then we search this area. And so on and so forth. And maybe if we still didn't find it, then we decide here for this direction. But if now a target was here, as soon as we find the target here, the walker stops and he has found the target. So that's now we want to know. So in the previous slide here, so we looked for the typical length of such a step and the number of steps we have to do until we found the. So now this means in order to find the search efficiency, remember the search efficiency was 1 over the average step length times the number of steps. Now we have to calculate what is the average step size and what is the number of steps. So let's first calculate here the average step size. But here the problem is we don't really have a power law distribution, but rather a truncated power law. Because now this depends on here the mean free length, the mean free flight distance. So I mean if the target is further, the next target is further away than the mean, than our step, so we can do the full step length. But if well, let's put it like this. I mean, so here when there was no target, there we can take the full step length taken that we have chosen from the power law. But if we found a target, we don't do the full step that we have chosen here, because then we stop, because we stop directly when we found our target. So in other words, so if our random number, our step length, if this is smaller than the typical free flight distance, then we do a full step. Of length L. But if this L is larger than the average free flight distance, so we want to make a longer step, we do only a step until the next target, and that's typically of the order of the mean step length. So step of length lambda. So, and that gives us a truncated power law. So we do only a power law until step L. And now if we want now to calculate the expectation value of the step length, so we have to integrate from our minimal, our cutoff, that's the search radius is our cutoff value, until the mean step length L. So that's the first case. And then we can really take the typical way to calculate the expectation, L times our distribution L2 minus mu dl. Yeah, but we don't integrate until infinity, because as soon as our step length from the power law distribution gets very large, and we know they get very large in the power law distribution, then so from the rest, from lambda to infinity, the step length is not L, but it's only lambda, and then we have the constant lambda times L2 minus mu dl, and then we have to normalize everything, and that's just the integral from R0 to infinity to L2 minus mu dl. And now we can plug in here our power law distribution and work out the integrals. And if you work this out, it's a nice exercise if you want, then you get this. Of course, this is not a formula you should memorize. This is more, I mean, this whole Levy search idea, I just want to show you as an application how we can apply all the details we learned about random walks and power law distributions here for some practical problem, like to find the optimal strategy to find a target. And if you plot this function, this average step length, as a function of the exponent mu, maybe I do this here. So make a sketch of the behavior. Here's mu. Of course, the range of mu goes between 1 and 3. That's the range of exponents in the power law distribution. Here we plot the average here step length, and then this depends on the parameter lambda, and here we do logarithmic scale 1, 10, 100, 1000, and then for a large free step length we have a function which goes down like this. So this would be for lambda about 1000, and you could imagine this are in kilometers if you want, if this would be units. I mean, so it's in units of R0 here, and if you have lambda equal 100, it would be like this, or for lambda equal 10, and this here lambda equal 10. And so you see, for if so the typical distance here decays with mu, decays with our critical exponent mu, and this means for very small mu we get very large typical distances, and this means then our search efficiency goes down, because our search efficiency goes with 1 over the typical distance. So this means too small mu, too small critical exponent, and this means we have a reduced search, inefficient search. And why is the search inefficient? Because we just make too long steps, and we take just too long to find the target. Yeah. So what's the next problem? So like we now calculated this typical step length, now we try to calculate the number of steps. How many steps do we need? So we want to calculate this n This here was in order to calculate this L here. So this was this calculation. Now we want to calculate the number of steps. And so how many steps do we need? And this depends now on the typical displacement of a Levy flight. And then remember, so we showed this in the previous so here when we looked at the mean square displacement of Levy flights, and then we have seen that the maximal distance of a Levy flight, in 1D, the maximal distance went with the time over 1 minus the critical exponent. Here it was alpha, now it's mu, 1 over alpha minus 1. Okay. But the same formula holds also for the typical distance that the walker in a Levy flight obtains in 2D. So we find that the maximal distance by the walker goes proportional to the time to 1 over mu minus 1. And that was here the time. And now we can reverse this. This means the time we need to reach a certain distance R max goes proportionally to R max over mu minus 1. And from this we can conclude that the number of steps to reach a target should go with the target in a certain distance r should go with the distance 2 power mu minus 1. Yeah? Of course, that's all very hand-wavy. And now what is this r here? This r depends now on the mean. So let's write it down. The number of steps we need should then go to this radius, and that's the typical length of the next target. So that's our step length. We have all of this in units of the search radius. So this should go for lambda over the search radius 2 mu minus 1. So then that would be the number of steps that we need to find the next target. But now there comes a small twist to the whole story. And the twist is this holds only for destructive search. This means once we have found a target, we need to find another target. So we need to go really a distance away. But what happens if we have non-destructive search? This means if we, for example, here was our last target. Now the walker has started to move a little bit to the side. We are here, maybe we did the first step. And now the question, how many steps we need to find the next target. But then we could of course also just go back. So we could just go back to our first, so like here was our previous target. Now we made a step, and now if we have non-destructive targets, instead of going many steps and find something else, we could just make a step back and go back to the target we had before, because it's non-destructed by the search. So this means the number of steps in non-destructive search is much smaller than in the case of destructive search, because we can just always go back. And now if you analyze this, And I don't have the time now to go through this, but if you look this, so you find that the exponent is just a half of the exponent of this. So this goes again with lambda over our search radius, but now with power mu minus 1 over 2. So it's just the square root of the number of steps we had with destructive search. And now we have all the ingredients together. We have the step length here, we have the number of steps in the case of destructive or non-destructive search, and now we can plot the search efficiency. This is if we just multiply these terms with this here. And now there's a cool result. So if we have destructive search, or let's say now we maximize the search efficiency. So now we want to know what is the exponent mu, so the exponent of our power law, which maximizes the efficiency of the search. And so you can just plot the search efficiency, so this function multiplied with this function, and plot this as a function of mu. And then it turns out, if we have destructive search, and then the optimal value is equals 1, so the smallest possible exponent, yeah, and that's basically the idea we had before. So if you have a search problem and just don't look twice in the same place, just always follow a straight line, just go straight forward, which means we make the maximal possible length of the Levy walk. So like you know in the power law with exponent mu equal 1, basically we just have one very long step. So for destructive search, basically never turn, just make long steps. But if we have non-destructive search, then if you plot this function here, so if you plot the search efficiency over our exponents mu from 1, 2 to 3, here's our search efficiency eta, and then it turns out the optimal search efficiency is found exactly for eta equals 2. Mu equals 2. This means the optimal search is one where the step lengths are taken from a power law distribution with an exponent mu, which is exactly in the middle of here the range. So how can we intuitively understand this? So I mean, it's kind of clear. Before we saw the step length for a very small mu is just too large, so the search gets for very small mu, the search is inefficient because the step is just too long. And for very large mu, so when mu goes in the order of 3, so here we approach kind of diffusive behavior. You know, when the power law in the Levy flight with mu equals 3, so we have diffusion. And then we just have too many steps, because then the step lengths also depend on mu. Here we have too many steps, and here we have too long steps. And then the optimal mu is given in the medium of the range. So that's a very classic result, and this is also a result which really renewed the interest in all these Levy flights, so that for Levy flights you can really calculate the optimal strategy to search a target. And if you want to read this up, so you can find this in a Nature paper by Viswanathan et al. This was in 2000, in 1999. So it's already some years. Nature. And so that's one of the classics in all the search strategy papers. So that's not this Viswanathan paper with the albatrosses I showed you before. That was a follow-up of the story, where the authors then showed that really Levy flights can optimize the search of random walks. So now with this outlook in optimal search strategies and Levy flights and Levy walks, now I want to leave the discussion of random walks, and I want to come back in the next lecture on these ideas about scaling. We've seen that in power law distributions were distributions which are scale-free, and we want now to see what does this really mean when we scale something. What does this tell us about the geometry and properties of objects? For the moment,